Today we're going to learn about power when it comes to electricity. Earlier, when we did energy, we learned that power, P, is equal to energy used divided by time. We did a quick lab on that where you walk up the stairs, found out your energy, this time it was gravitational potential energy, for a flight of stairs, and timed it. Then we took our total amount of energy, we divided by time, and we came up with power. And our units were watts. W-A-T-T-S. All right. So watts are the units for power. You probably noticed that when you look at a light bulb is designed to have certain power output in watts. So you might have a 60-watt light bulb, a 100-watt light bulb. Oftentimes you'll look at other appliances, and appliances will give you a power rating too. Like your microwave might be 900 watts, or a curling iron might be so many watts, 800 or 900 watts. A stereo system might have a certain output, like 150 watts per channel. So let's look at how we actually come up with power for electricity. So we know two things so far. We know that we have current, I, all right, and the units for current are equal to coulombs per second. And we also have voltage, and voltage is a joule per coulomb. Well, this doesn't look like much yet, but what we want is we want to find energy divided by time. So if we look at current, all right, which is charge per time, all right, and we look at voltage, which is energy per charge, all right, we can simplify these guys. These should be Q's. All right, so let's look at this. So we have current, which is charge per time, and voltage, which is energy per charge. So we need energy and time. So let's solve this one for charge. All right. So if we solve this for charge, we get Q equals current times time. All right. So now what we need to do is solve this one for energy. So energy is going to be voltage times Q, which equals energy. All right. Now we have an expression right here for Q. It's I times T. So I'm going to substitute in my Q right there. All right. So if I substitute in Q, I get voltage times Q, which is I times T, equals energy. All right. So what do we want? We want energy per time. So if we divide both sides by time, we get V times I equals E over T, which is power. All right. So power in electricity, power equals V times I. Now somewhere along the line, probably when I was in high school, we used power equals IV, and for some reason my teacher taught me that the way you remember power is poison IV, PIV. All right, so there's our equation for power. So we multiply our current times our voltage, and that's going to give us power in watts. Another thing we want to look at when talking about power and electricity is energy used or energy converted. So we know that power, P, equals energy per time. All right. So if we multiply both sides by T, all right, we'll end up with energy equals power times time. So it's important to be able to calculate energy because that's what we buy from the electric company, Commonwealth Edison, for most of us here. So our energy that we buy from Commonwealth Edison is basically the power that we've used in the month times the amount of time we use that power. For example, if I use my stereo that uses 100 watts times time, I can find out how much it costs me to use that stereo. All right, so let's take a look at that. If we do multiply power times time, all right, power is in joules per second and times is in seconds. All right, so if I operate an object that say has 100 watts, so power equals 100 watts for 1 minute. Actually, let's not go for a minute. Let's go for an hour. All right, so for 1 hour, let's take a look at how much power I have. So the power would be 100 watts times time in seconds. Well, there are 60 seconds in a minute and 60 minutes in an hour. That gives me a grand total of 36,000,000. All right. 360,000 joules. Well, that may sound like a big number, but it's really not all that much. When we calculate energy for, power consumption, all right, we actually use a different units because we don't want bills and stuff, and we don't want numbers that are really huge. It's very common to use units that are a little bit easier to look at. So what we do is when we calculate power, we'll go power equals energy times time. All right, and that is equal to, we convert our energy to kilowatts, all right, 1,000 watts, times time in hours. All right, and so then the unit just becomes kilowatt hours. Electricity around here costs about 10 cents, maybe 12 cents per kilowatt hour. So to do this problem would be a whole lot easier using kilowatt hours versus joules. So let's go back and do this problem. So to do our problem with kilowatt hours, all we do is we say power is energy in kilowatts times time. Well, our energy was 100 watts. So energy is going to be 100 watts, divide by 1,000 to get kilowatts, times 1 hour. So that gives me 0.1 kilowatt hours. Now, what did that cost? That's what we're really trying to find out. So the cost is going to be 0.1 times, about 10 cents. So that's $0.1 per kilowatt hour. So it's going to cost $0.01. to operate that item. So, although this looked like a really huge number, it really wasn't that much when it comes down to the cost of actually operating something. So let's go through the example that you just did with the problem number 7 on your intro to power worksheet. So problem number 7 says that we have a 60 watt bulb that operates at 120 volts. So power equals 60 watts. The 120 volts is just your normal household power, or I'm sorry, just your normal household voltage. So that doesn't really matter. Then the rest of the problem tells us our local power utility sells energy at 8 cents per kilowatt hour. How much does it cost to leave the light bulb on for the whole month? So we're going to leave the light bulb on 24 hours a day for a whole month, and we're going to find out how much that costs us. All right, so here we go. We're going to take we're going to take energy equals power times time, but we need the energy in, we need the power in kilowatts, and we need the time in hours. So energy used is going to be power in kilowatts, so 60 divided by 1,000. All right, now we want our time in hours. So what we're given with is we're given 1 month. I'll call it a M for a month. All right, we need to convert months to days. So we'll just assume that there's 30 days. So 30 days per month. And that cancels. Now I'm left with 30 days. So what do we know? We know that there are 24 hours per day. I'm going to cancel days. All right. And then calculate all that out. So we multiply everything across the top divided by everything across the bottom. And that gives me 43.2 kilowatt hours. So what's our cost? Our cost is going to be 43.2 times it's 8 cents per kilowatt hour, 0.08. It's $3.46. So it'll cost you $3.46 to run a 60 watt light bulb for 24 hours a day for a whole month.